All right. This is our final talk of this session. Will be given by Claudia. Claudia, whenever you're ready.
Thank you. Can everybody hear me? Okay, good. Thank you, guys, for being here just before the break. So my name is Claudia, and I'm going to introduce you to some observation of collective bistability that we have observed in a nonlinear resonator array. Okay, so this work has been done at Chalmers University, which is a university in Sweden, in the north of Europe, at the 22Q lab. This work has been done under the supervision of Simone Gasparinetti, and I would also like to thank my two theory gods, like Theo and Timo. So let's start with dissipative phase transitions. Dissipative phase transitions happen in nonlinear quantum open systems. They happen when we have that the steady state of our system changes abruptly when we are changing a control parameter. Okay, so here I have the, so as you can see, we have the steady state. In this case, it's in the X, it's in the X-axis, and then we have our control parameter in the Y-axis. Well, what we can observe is that at some point, our steady state will just suddenly jump to another steady state. In this region, we have that two metastable states exist. So this comes from looking at the time evolution of our state, where we have the steady state and we have some time evolution. Then what we observe is that the lambda, it's our Liouvillean gap, which determines our relaxation rate to the steady state, will also change depending on the control parameter. So now we again plot the control parameter on the Y, and the Liouvillean gap on the X. What we observe is that at some points, our state will come to this steady state, and another one we will have that it goes to this steady state, and at the critical value of our control parameter, we will have that our system coexists in two states at the same time. This is what it's called first order transitions, and we have different signatures of this behavior. The first of them is that we will have this abrupt jump in the steady state, then that we will have a bistability around the critical value where the two states will live at the same time, and that we will have that the time scales of our decay will be slower than the intrinsic relaxation time of our system because of the Liouvillean gap going to almost zero. So now let's look at what was done before. We have that these systems, this has been studied in previous systems like Kerr resonators, where we have that the transition rate, slowest one, have been like 50 megahertz approximately. Then these studies have also been done on a linear resonator coupled to several qubits. And finally, they have also been studied in linear resonators arrays that are coupled to nonlinear qubits. The slowest transition rate that they have recorded is 10 hertz. However, none of these systems have studied what happens when we have that the nonlinearity is in our resonators, which will produce some collective transitions. So let's start with our device. Here it's a device where we have that we are done this in a superconducting circuit. We have in blue 21 resonators. If we focus now on these resonators, we have that they are composed of a capacitor that is shunted to ground, and then we have an array of Josephson junctions, which will give some nonlinearity. This corresponds, if we go back to the schematics that I used before, to a system where we have all our nonlinear resonators coupled to each other by J, and the nonlinearity is in the resonators in this case. So now let's characterize the device. For this, we first look into the linear response of our system. We will send a probe tone through the input, and we will read at the output what is coming. What we observe, if we look at the transmission, then is that we will have 21 peaks that corresponds to the 21 resonators that we have in our system. And these peaks are all in a transmission band between 5 and 6 gigahertz. This system is usually modeled using a tight banding model, where we have that our modes are equally spaced in the center, and then they get concentrated at the band edges. Now let's look at our nonlinear response. For this, what we have to do is that we will be changing the power of our probe from low to higher powers. And we will be looking at the center resonators, at the center resonator. So we will model our system only looking at the center resonator, as a resonator is coupled to input and output ports and has some decay. The transmission spectrum will follow this equation that then we can plot here, where we have from lower values, where we see that our transmission spectrum is symmetric, to higher values of power, where we see that our spectrum starts to get a tiny bit squeezed to the left. This comes from the nonlinearity, which in our case, it's around 211 kilohertz, and our total decay is 630. So now let's look at what we came here for, that is these collective phase transitions. We have our probe again, we will look at what comes out, and now we add a second tone, that is a pump. What we will do is that we will sweep the power of the pump from low to high powers. So then, when we look at our transmission, now we have, at the bottom we have the frequency of our probe, and we have in the y-axis the frequency of our pump. So then, at low power, we don't expect anything, so we only see our 21 peaks from the 21 modes. Now, if we go higher in power, what we observe is that when the pump frequency crosses or it's close to any of the modes in our metamaterial, we will have a sudden jump in all of the modes at the same time. If we even go higher in power, then we observe that some modes start to disappear. So now that we have seen the jumps, let's look at if we have some hysteresis in this. For this, we will tune the frequency of our pump from low frequency to high frequency, where we have that our transition from one of the states to the other one will happen at this frequency. And now we do the same, but from high frequency of the pump to low frequency of the pump. What we observe is that there is some difference in these two values that it's because of the hysteresis. The hysteresis is a feature of the bistability of the system. Finally, we will look into the time dependency of these measurements, how this system jumps between the two states. For this, we again look at the transmission between the different modes, and we do a cut through that mode. Then, if we are tuning the pump frequency, we will select the frequency at which we see that the transmission changes in frequency, so this point. And we will look at the modulated traces of all of our different modes at the output of our system. What we observe is that all of the modes are jumped at the same time. If we now do a PSD of this signal, we obtain that the jumps happen at 0.6 seconds, which is way higher than the intrinsic decay of our system. So as conclusions, we have seen this collective bistability. Then we have looked at the hysteresis of it, and we have shown some time traces. In the future, this could be studied for doing some critical cut or some critical sensing. Thank you.
Well, I think we have time for questions. If you have any, please come up to the microphone.
Very nice talk. Like, do you plan to tune the nonlinearity of the modes by bringing the qubits? Because you had 2 qubits on your chip here. Like, you could tune the qubit closer to the eigenmodes and see like how higher nonlinearity changes these dynamics, for instance.
We have introduced the qubit into the system, and we see that the feature is a tiny bit different, but we cannot explain it. So we have decided to just stick to the array of resonators.
Okay, yeah, thank you.
Maybe you can hear me. What's the critical cat qubit? And why would that be interesting to do it this way?
So there is a paper out already on PRX, and you have the dispersive cat qubit where you are like sending a probe, well, a pump that will like squeeze your states. So they think that by sending this pump detune and getting into this bistability regime, because your rates are slower, then you will have the cat more protected.
Thank you.
Okay, let's thank our speaker again, and every speaker actually in this session. And yeah, this should be it.
Thank you.